Welcome back, everyone. We're going to continue today with Chapter 3. We're on Section 2. And our topic today, we're still talking about data description. And Section 2 covers what are called measures of variation. So measures of variation, if you remember in the first section, we were talking about measures of center. So when you're looking at a data set, measures of center like mean, median, mode, and mid-range describe where the middle of the data, where the center of the data is. Measures of variation are a way to discuss how spread out or compact the data is. So the data can be, all fairly close together, or you could have a wide range of values where the data is very spread out. And that's what the numbers, the values that we get from these measures of variation talk about. And so we're going to talk about the measures of variation, as we said, such as the range. That's the first one we're going to talk about. It has a very easy computation. The variance, which is a little harder computation, but it has a lot more nuance to it, it's better information for a researcher to have. And then the standard deviation. And the standard deviation is just one extra step after computing the variance. So it's also pretty easy once you have the variance done. So let's move on to our first example. So our first example here, we're going to be talking about two brands of paint. We have brand A and we have brand B. And this testing lab, we're going to treat these two brands as if it's the entire population of paint. So as if there's no other cans of brand A besides these 6 gallons of paint. So there's gallon 1, 2, 3, 4, 5, 6 of brand A, and then 6 gallons of brand B. Now, why do we want to do that? We want to do that because computing the variance for a population is a little bit easier than, well, it's not easier, but it's a little bit more understandable as to where it comes from than for a sample. So for now, we're just going to treat it as if, because it's a testing lab, this is the entire population. There don't exist any more cans of brand A. So just these 6 cans are the only 6 cans of brand A that there are. So this is the entire population of brand A. And then if we look at the second one, we're going to treat it the same. So we're treating this as if this is the, and I'm going to add up here. So this is the entire population of 6 gallons of brand A. And same thing here, this is the entire population of 6 gallons of brand B. So there don't exist any more gallons of those paint types anywhere else. So now that we've kind of established that, let's look at what the mean of both of these brands happens to be. We can tell, let me erase this so I have some room here. So we can tell that these two brands definitely are not identical in their information. Brand A has 1 can, and what we're measuring here is how many months it lasts before it fades. So this first can here where it says 10, that means that first gallon of paint, when they tested it, it lasted 10 months before it faded. And then the second one lasted 20 months before it faded, and so on. Now you can see here that every value is different. We can also see that we have as low as 10 and as high as 60. And so that's brand A. But if we look at brand B, we have some repeats. We have a couple 35s. The highest value, were nice enough to put it in order for us. The highest value is only 45 and the lowest value is only 25. So what do we get when we average these? Well, if I add up 10 plus 20 plus 30 plus 40 plus 50 plus 60, I get 210. And if I add up 25 plus 30 plus 35 plus 35 plus 40 plus 45, I also get 210. So when I add these two data values, each of them get the exact same sum. So when I compute the mean, remember to compute the mean, you're going to take the total, which in both cases is 210, and you're going to divide it by how many there are, which in both cases is 6 gallons. So if I divide 210 by 6, I get a 35-month average before each of these brands starts to fade. So the mean for both brands is the same. There's no way to tell any difference by just looking at the mean, but we can clearly see that these two brands are different, that they behave differently. So why is that? What does that mean? Well, the reason that they behave differently is because they have different variations. So if we look at brand A, they have this kind of visual for us down here. You could see we have a can at 10, a can at 20, a can at 30, a can at 40, a can at 50, a can at 60. And so if you average those, this is all symmetric, the middle of that, the center of that is at 35. And if we look at the other brand, we have 25 and 30 and 35 and another 35 and another and a 40 and a 45. It's still symmetric, and it's still symmetric about 35. And so that's why the average for this one ends up being 35 also. But again, we can tell by looking at these two picture graphs that A is much more spread out in its numbers than B is. B doesn't even have 10 marked on the scale, and actually their numbers down here on the bottom are much closer together. So that kind of accentuates it a little bit too, but we can tell that this is very clustered around 35, whereas this is spread about 35. And so they're going to have different measures of variation. So what is the first measure of variation we're going to do is range. And that's the one that I said was very easy to compute. So I'm going to leave this so we can see it. So up here, to compute the range, all you do is you take the high value minus the lowest value. So in the case of brand A, remember our highest value was 60, and our lowest value was 10. And so 60 minus 10, we get 50 months for the range. If we do the same thing with brand B, we already know it's not as spread out. It only goes with a high of 45 to a low of 25. And so if we do 45 minus 25, we get 20 months for the range. And so, as we mentioned, when you have a higher measure of variation, you're going to have data that is more spread out. When you have a lower measure of variation, you have data that is more compact. So the measure of variation for the range, the one problem with range, even though it's wonderfully easy to compute because it's just the high minus the low, it only uses the high and the low values. It doesn't really care about anything in between. So the 4 cans that are in the middle here for brand A they aren't taken into account at all. We don't know if they're all down by the 10 or if they're all up by the 60 or if they're spread out like they are. All the range uses is the high and the low. So, and then of course the same thing with the brand B. We only use the 25 and the 45. It doesn't take into account these ones that are in the middle, that we don't know if these are all close to 25, all close to 45, or if they're kind of spread out like these are. So when you do the range, the one problem with it is that it only takes into account the very highest and the very lowest values. So how do we do better? Well, we do better by computing what is known as the variance and the standard deviation. And when we do the variance and the standard deviation, they take all of the values in the set into account. We use all the values in that set to do the computation for variance and then use that for standard deviation. So what does deviation mean? We talk about the standard deviation. So both variance and standard deviation are based on this idea of a deviation from the mean. Think about the English language. In the English language, when we use the word deviation or deviant is kind of a term that used to be used. It's kind of a derogatory term, so it's not really used anymore, but it used to, when somebody was called a deviant, it was someone who committed crimes or got into trouble or did things that weren't acceptable to society. So deviant, and then if we talk about it more in modern day terms, someone might say, you know, the results deviated from what we expected, or they deviated from what we've gotten in the past. So the idea is that deviate or deviation means to be away from the typical. Well, what is typical with our brands of paint? Well, the mean. The mean is kind of considered the typical. So the mean was 35. And so we're going to look at that as the typical and see how each of the different cans in each of the brands deviates. What's the deviation from that mean? So if we look at brand A and we look at this first gallon, this first 10, or the first gallon that was at 10 months, and we calculate the deviation, we do that by saying 35, well, hold on, did that backwards. It's actually 10 minus 35. So we take what the value was and we subtract the mean. And in this case, we get negative 25. What does that mean? That means that that gallon performed 25 months less or below the mean. So what does that mean for the, for the paint? Well, that particular gallon might consider it a bad gallon or an underperforming gallon or something like that. And then we continue that all the way through. So 20 for the gallon that was what lasted before it faded for 20 months, 20 minus 35 is negative 15. And so it performed 15 months below the mean. And then we do the same thing for the 30 and the 40. When we get into the positive numbers, you see values such as the 50, which if we do 50 minus 35, we now get a positive number because that gallon performed 15 months above the mean, above what was the typical expected length of time. So brand A, as we mentioned before, it's much more spread out. So it has gallons that go everywhere from 10 months to 60 months. So in advertising, let me go back up here a little bit. So in advertising, if we were looking at these two brands, advertisers would probably be more happy with brand B because they could say it was more consistent. It was more reliable. These are terms you hear a lot in advertising. Our brand is reliable, it's consistent. And if you were trying to promote the other brand, you might talk about, it lasts as long as 60 months. They could do that, but then they would be dishonest if they didn't also say that it could last as long or as few months as 10, but they probably wouldn't say that because it's advertising. So for brand A, they might say it lasts as long as 60 months. So that's the kind of thing when you're hearing advertising, listen to what they're actually saying. When they say it lasts as long as 60 months, they're not saying that it lasts 60 months. They're saying that at some point, one of their samples lasted 60 months. But if you hear consistent, reliable, they might say something along the line for brand B that it's will last from 25 to 45 months, or they might say something like it lasts at least 25 months, something like that, before it fades. All right, so now let's go back up to figuring out how we do this variance and standard deviation. So we have the deviation from the mean for all of brand A's gallons. If we were to right now add up these deviations, we would get 0, because every gallon on the left side with a negative value has a matching value on the right side that would cancel it out. So negative 25 and 25, negative 15 and a 15. So if we added those up, we'd just get 0. Now, it's not always that it's this perfect, but it would be that if we just added up the deviations, the negatives would cancel out the positives. So, you know, it might not be perfect like this, but you might have something like negative 20, negative 20, negative 5. So where one was lower, but then the next one was higher. So they still total negative 45 on one side and positive 45 on the other side. So that's not going to be very helpful, because that's not going to tell us how the data varies by just adding up those deviations. So what can we do to get rid of those, or to have something that isn't affected when we sum them up with the negatives and the positives to just get a 0? Well, what we do, or what researchers have decided to do, or mathematicians, is they said, well, since we want to kind of get rid of this negative problem, let's instead look at the squares of the values. So instead of looking at negative 25, let's look at negative 25 squared. Instead of looking at negative 15, let's look at negative 15 squared. Because if you remember, when I take something and I square it, we're always going to get a positive. And I'm going to pause here for just a second and kind of do a little bit of an aside on calculator work. So if you take on your calculator, hold on one second. If I just were to type in or compute on the calculator negative 5 squared, order of operations would actually, a different color here, would actually do the 5 squared first. And that would get you negative 25. Because it would do the 5 squared, which is 25, and then it would just plop the negative in front of it. That's not what we mean. When we say we want to square negative 5, what we mean is we want to take negative 5 times negative 5. And if we want to do that, then on your calculator, what you're going to need to do is you're going to need to do a parentheses, negative 5, and then a square. So let me pull up this little calculator emulator that I have on my computer. This is like a Texas Instruments handheld calculator. And while we're talking about calculators, let me talk about a couple things as far as like when we get to I know we're a little bit away from it, but when we get to the test, you're going to need to have a handheld calculator. There is a calculator available within the test, but I don't get to select what calculator it is, and the one that is within Respondus is just very bare bones. It is a scientific calculator, but it's not the best scientific calculator. And of course, you can't use your phone during the exam. So you're welcome to use your phone for your homework and such, but when it comes to the exam, you either have to use the one that's in Respondus, which isn't a great calculator, or you need to have a handheld regular calculator. So and you're going to have to show like your workspace before the exam. So if you're taking it online. So go out and find yourself a calculator. I have some recommendations in D2L. It doesn't have to be anything super expensive. You can get the TI-34s or I really like the Casio calculators. I wish I could find an emulator for the Casio calculator that's good, but the Casio calculators that are like FX something, I really like those. And there's examples of them in D2L if you want to go look. But and you can borrow it from somebody. You can even come and borrow it from the library, because we do have ones to check out from the library on campus. The Learning Center, I think you can get them, I think you're supposed to only check them out for 4 hours. But again, you can get them for fairly cheap. I think the TI-34s and the Casios run between like $12 and $18. You don't have to spend any more than that. If you have a graphing calculator, that's perfectly fine to use, but you don't have to go out and buy a $100, $125 graphing calculator. It's not going to help you in this class in any way. We don't use it for that. But the graphing calculator does have all the scientific calculator functions on it. So if you have a graphing calculator, you're welcome to use that. If you have any other standard scientific calculator, it'll be fine. Okay, so back to what we were talking about mathematically. So if you want to put in -5 squared, we want to use a negative sign. And on most calculators, the negative sign and the minus sign are not the same thing. So don't use this button, okay? Use the button, it usually has like a parentheses around it, or sometimes it'll be like plus, slash, minus, something like that. But you want to find your negative button. And then you're going to push your 5, and then your power, I'm going to do it wrong the first time. For your power, I can either just push the x squared button, which will put a square on it, or I can use this little up arrow looking thing. It's called a caret, and it basically is saying I'm going to put the number up like a superscript, and then I can put a 2. The nice thing about that is it lets you put anything up there that you want. So when you push that button, it has a little box up there, and then I could put in a 7, or I could put in anything I wanted. So the nice thing about that caret is knowing that. Now on the Casio calculators, let me minimize this. On the Casio calculators, they often, for a lot of these things, will have boxes. So for the power button, it'll have something that looks like this on the button. It's basically saying you'll have a number here, and I'll let you put a number up here. If you're trying to do a fraction, it'll give you a button that looks like this. And so the Casio calculators, it's kind of a more visual button, whereas on the Texas Instrument, it uses kind of a standard. This is standard on computers and stuff. This up thing that's called a caret is pretty typical. Okay, so now we've got our, and if you have your calculator now, I highly recommend that you go ahead and practice this. If you don't have your calculator yet and you're just using your phone, make sure that what you're using on your phone is a scientific calculator. You can download all kinds of free ones from the app stores. And make sure you're using a scientific one, and still go ahead and practice it, because you're going to need to have it on your homework. So in this case, though, remember I said I was going to do it wrong. So if I do -5 squared and I hit enter, that's going to give me -25. But that's not what I want. I don't want -25. What I want is -5 times -5, which is 25. So how do I do that as a square? Well, the way I do that as a square is I make sure I put parentheses around the -5. So parentheses -5, parentheses, and then I can do the square or the square like this. Okay? And then hit enter or equals, and it knows, oh, they mean -5 times -5. So there's just a little start to the scientific calculator. And I'll try to show you these kind of as we do things, because if you can't do the work on your calculator, it makes it really hard to do your homework. All right. So how do we calculate population variance and then use that to get population standard deviation? So there are some notations here that look kind of scary, but we'll learn what they all mean. Remember, we already had the symbol mu, which we know is the population mean. And so that's what this number is. So to get the population variance, you're going to take x, which is one of the values. You're going to subtract the mean, and then you're going to square it. Well, that's what we're just doing. So when we had our values up here, when we had the 10 minus 35 and got the negative 25, or the 30 minus 35 and got the negative 5, those were that was the inside values here. That was our x minus our mu. Then we're going to take all of those and square them. And then remember, this big E looking thing means sum. So we're going to sum up each value minus the mean squared. So we're going to take all the values minus the means, we're going to square them, and then we're going to add them up. Once we're done, we're going to divide by the number in the population. So in our case, our population, remember, was 6. So in our case, we would divide by 6. Now, there's a new variable here that we haven't used before, and that's this one right here. So that is the population. Remember, we talked about if it's a Greek letter, it's almost always population. So that's the population variance. And it's read as sigma squared. So we could call it sigma squared, or we could call it the population variance. Now, what the next formula you can see, it looks almost, let me get rid of some of this messy stuff here. I'll just get rid of these arrows here. Okay, so when we get to this next formula here, you can see that this formula looks exactly like this formula, except it has a square root bar over it. Okay, so it has this square root bar that goes over it. So what does that mean? That means that we do this kind of a little bit lengthy calculation to get the sigma squared, but to get the population standard deviation, which is just the sigma, all we have to do is, and again that's called sigma because it doesn't have the square on it, all we have to do, what do we do when we have something squared and we want to get the square off of it? Well, the opposite operation of squaring something is taking its square root. So all we have to do is take what we got up here and take the square root of it. So if we take the square root of sigma squared, we get sigma. So like I said, this is the hardest thing that we have to do, is getting the variance. But once we have the variance, getting the standard deviation is super easy. We just do the square root and we're done. And I'll show you how to do that on the calculator when we do it on this next example, or on the example with the actual numbers. All right, so now we're going to do the actual calculations for this. So to take the numbers that we had before, remember we had these two columns already. We had taken the actual value, the 10, and subtracted 35, and we got the negative 25. We took 20 minus 35, and we got the negative 15, and so on. So now for this, all we're going to do is we're going to take those numbers and we're going to square them. So negative 25 squared, if we do that on the calculator, pop that up really quick again. So if we do parentheses negative 25 squared and hit equals, we get 625. So that's where that 625 in the next row came from. If we do negative 15 and we square it, then we get 225. So parentheses negative 15 squared, it equals, we get 225. Then when we get over to the positive ones, we don't have to use the parentheses anymore because we don't have to worry about that negative. So for instance, when we do just 5 squared, we just do 5 squared. Don't have to worry about the parentheses in that case. And that'll give us 25. So you can see they've done that for each of these. So negative 15 squared is 225. Negative 5 squared is 25. Then we do 5 squared, which is also 25. And we do 15 squared, which is also 225. And we do 25 squared, which is also 625. And so now you see we don't have any negative values. All this last row is all positives. And now we're going to add all of those up to get the top number. So let's review what the formula said. So the formula said that we are going to take the sum of, which is the last thing we're going to do, the x minus the mu's. So the x minus the mu's was row 2 here. That was the actual value minus the mean. Then we squared them all. So the square, that was this row. But now that big sigma says we're supposed to add them all up. So we're going to take all of those values and we're going to add them up. So I'm going to take 625 plus 225 plus 25 plus 25 plus 225 plus 625. And if I add those all up, I get 1,750. That's this number on top. And then when I'm done, after I've gotten all that calculated, I divide by how many values there were, which was 6 gallons of paint, and I get a variance of approximately 291.7. So let me pull that up as far as for rounding purposes. So we take 1750 and we divide that by 6 and hit equals, and you'll notice it comes out to be 291.66 repeating, and we're going to round that because we want to round it to 1 decimal. So we have the 1750 divided by 6 got us 291.66666 and so on. But we only want to round it to this place because we want to go 1 decimal past the whole numbers. And we look to the right and we say, oh, following that 6 is another 6. And that 6 tells me that I should round this up. I shouldn't leave it 291.6. I should round it up because 66 is closer to 70. So I round that to 291.7. However, leave that number on your calculator. Don't take that off of your calculator. Remember, whenever possible, we want to not round anything until the very end. So I can go ahead and write that down for my answer for the variance, but I'm going to leave it in the calculator so that I can use it for the calculation for the standard deviation. And I'm going to show you another really, really useful thing on your calculator. If you have a number on your calculator and you want to use it in the next calculation, you can use this answer button. You'll notice on mine, though, the answer is up above on this button, this one right here. And I don't want the negative, I want the answer, the ANS. And so what I'm going to do is I'm going to clear out what I have, and then I'm going to tell my calculator I want to do the square root, so I have to hit second square root. I don't know if on your calculator it'll be a second. You have to look at your calculator and see is the thing that you want to select up above the button or at the top of the button, or is it actually on the button? It'll be like color coded. So for instance, I have a Casio here that I'm looking at. You have to hit Shift. Actually, you don't. On this Casio that I have, there's just a button for the square root. So you just hit the square root. But if you do want something that's up above the buttons, you have to hit the Shift. Okay? So once you find that and locate that, then you're going to put, hold on a second, done something with my, okay. Then you're going to put the answer in there from the prior problem. So if I hit, on this calculator, if I hit second and then I hit this button, it puts ANS up there. ANS means the answer from the prior problem. And so it's going to put in that 291.66666 repeating the whole thing into my problem without me having to enter it. And then I hit enter and it tells me, oh, that comes out to be 17.07. Again, rounding properly, the 0 is where I want to round to, but after the 0 there's a 7, so I'm going to round that up to 1. So it comes out to be 17.07 something. But I want to round to this spot, and the number right after the 0 is a 7. That 7 says don't leave that as 0, round it up to 1. In other words, 0.07 is closer to 10 than it is to 0. So I'm going to round it up to 17.1 months. So we just did our first standard variance and standard deviation. So the standard deviation is 17.1 months and the variance is 291.7 months. It's actually square months, but we won't go into that. Okay, so if we do the same thing for the other brand, for brand B, when we do these calculations, you'll notice, remember we said this data wasn't as spread out. And so you'll notice that we got considerably smaller numbers when we did this. So if you take, 25 minus 35, you get -10. And so that first gallon only performed 10 months below the mean. Remember, the 35 is coming from the fact that that was our mean, okay? Then we have 30 minus 35. So while it performed below average, it was only below average by 5 months. Then we have 2 gallons that were actually right at the average. The other brand didn't have any that were average. They were either above or below. But this brand has 2 that are right at the average. So when I find their deviation, how much were they different from the average? They weren't different from the average at all. So I get 0 values for those. Then 40 was 5 months above average, 40 minus 35, and 45 was 10 months above average. So we get much smaller values because they weren't spread out from the mean as much as the other brand. So I'm going to do the same thing. I'm going to square those. So -10 squared gets you 100. -5 squared, we already know, is 25. 0 squared is 0. 0 squared again is 0. 5 squared is 25. And 10 squared is 100. So to go from the second row to the third row, you just square them. And then the formula says, once you've subtracted them all from the mean, or subtracted the mean from all of them, and you've squared them all, then add them up. So we're going to do 100 plus 25 plus 0 plus 0 plus 25 plus 100. And that gets us only 250. Remember, before we had 1750. So we get 250 as the sum of the squares of the differences, and 250 divided by 6 rounds to 41.7. Pull the calculator up real quick. So 250, clear this out. So 250 divided by 6, I get 41. I have 6's repeating again, so that rounds to 41.7. And then to get the standard deviation, I just take the square root of the answer. And again, that's the answer from the prior problem. And so second answer, oops, something didn't happen right. Let me try that again. Square root, and then of the answer, there we go, hit enter, and we get 6.45, so the 4 rounds up to 5 because the 5 is bigger, the 5 or bigger we round up. So don't leave it 6.4, round it up to 6.5. And you'll notice that we get a considerably smaller variance and standard deviation for brand B because it had a lot less variation. So we had 17.1 months for brand A, and we had 6.5. So 17.1 was the standard deviation for brand B, or for brand A rather, and the standard deviation for brand B was 6.5. So that means that 6.5 is smaller, so it has much less variation. And remember, it had a smaller range too. It only had a range of 20 instead of a range of 50. So another indicator that that has less variation than the other brand. So if we were going to do this again for a sample, we have very, very similar formulas. You'll notice here we have the sum of, and we have x minus x bar, and we square it. Remember, x bar was the sample average, or the sample mean. So you're still taking the value minus the mean, but now sample mean is x bar instead of mu. We have this number in front that's, or this variable in front that still has a square on it. S squared is the sample variance. And then S, if we take the square root of that, if we take the square root of the S squared, we get S, and that is the sample standard deviation. These are all these ones that we've talked about today, the sigma squared and the sigma, you should add those to your cards that you're practicing. So you should have, for instance here, you should have a card now, add to your little card set, on one side an S squared, and on the other side it should have sample variance. And you can do this in some sort of program too. You can use, I think, Quizlet or something like that to make flashcards to practice, or you can just do them by hand. A lot of people, if you have it in your hand, that's a different type of learning. It actually activates like your tactile learning because you're touching them. So if you're kind of a person who, when you can get your hands on it, you remember things better, I'd recommend doing cards that are physical cards, just some little note cards. You can make them out of paper. You can actually buy some index cards, whatever works. You've just got to get these few terms down on something that you can look over. And then, of course, you're going to have a card that has the S, and then on the other side you're going to put sample standard deviation, and then do the same thing for the sigmas. So you'd have one for sigma squared and one for sigma, with population variance and population standard deviation. Okay, so what's the one thing that is different here? Well, the one thing that is different here is that when you're talking about a sample, we divide by n minus 1 instead of n. And little n is the sample size, and we subtract 1. So whatever the sample size is, you divide by 1 less. The reasoning why I'm not going to go into it too in depth, and I don't know actually the details as to why, but I do know that the reasoning for it is that it is an adjustment for the fact that you're looking at the sample instead of the whole population, and the sample isn't as good as having the whole population. So by subtracting that 1, it's an adjustment for the fact that you're using a sample instead of the population. Okay, so let's look at a really quick example of this. So it says we've got 5 randomly chosen bags of candy that have 34, 38, 39, 41, and 43 pieces of candy in them. So, you know, say somebody put together some little goodie bags for a wedding or for a kid's party or something like that, and they were trying to keep them about the same, but they didn't measure them perfectly. And out of these 100 bags, you grabbed out 5 and you counted how many there were. Well, you took a sample of 5 from the 100. So now you have a sample. So in order to do the standard deviation, the variance and standard deviation, the first thing we want to do is compute the average. So the average is 34 plus 38 plus 39 plus 41 plus 43. And then we're going to divide that by 5 because we had 5 bags of candy. And that comes out to be an average of 39. So 39 is our sample average. Now we're going to do the deviations. So we're going to take each of those and we're going to figure out how far are they from average. So the first bag was 34. We subtract 39 and we get -5. So that first bag of candy, the one that had 34 in it, was 5 below the average. The next bag of candy at 38 is 1 below the average. 38 minus 39 is -1. The next bag was, we've done the 34, we've done the 38, we're on the 39. Well, that one was spot on. That one was right at the average. So 39 minus 39, you get 0. Then we have 41 minus 39. We have a bag that's 2 above average. And then we have another bag that's 4 above average. So the person that got the 43, we've done the 39, we've done the 41. So the person that got the 43, they had a bag of candy that was 4 pieces of candy above the average. So 4. And again, remember, if I add these up, I'm just going to get 0. So that's not going to be much help. -5 plus -1 plus 0 plus 2 plus 4. There's -6 below the 0 and there's +6 above the 0. It would just add up to 0. So that's not going to be helpful. So instead of doing that, we're going to take the squares. So we've got -5, -1, 0, 2, and 4. And we're going to make our, that would be like our second row that we had up above. We did figure out how to do a straight line on this program, which I'm ecstatic about. Here we go. Okay. And then when we do -5 and we square that, that's 25. -1 squared is 1. 0 squared is 0. 2 squared is 4. And 4 squared is 16. So that's where these numbers came from. And if we add those up, we get 46. That's going to be our top number in our formula. So they don't show the whole formula here. Just have the numbers. So we're going to plug them into this formula. We're going to take the sum of the difference of the mean and the values squared. So we need to sum these up. And that's this top number. So S squared equals the sum of the x minus the x bars squared. And then we're going to divide by n minus 1. So in this case, the sum of our x minus x bar squares came out to be 46. And then our n minus 1, we had 5 bags of candy, so 5 minus 1 means we're going to do 46 divided by 4, which comes out to be exactly 11.5. So our variance for those 5 bags of candy, for the bags of candy, is 11.5. And then to get the S, we're going to do the square root of 11.5. which comes out to be about 3.4. So if we do the square root of 11.5, we get 3.39, which rounds up to 3.4. So that is what we call the theoretical formula for doing the sample, the variance and the standard deviation, whether it's the population variance or the sample variance and standard deviation. However, there is, when we're doing variance and standard deviation, we're almost always doing it on a sample. Remember, the reason we did the first one the way we did with the population was because it's a little bit easier. We just had the n instead of the n-1. So most of the time we're doing the variance and the standard deviation for a sample. And the good news is there's actually a shortcut method for doing the sample variance and the sample standard deviation. Now, let me kind of tell you that this is actually one of the most complicated calculations you're going to do in the class. And I know it's a little tedious, it's a little time consuming, but if you practice those steps, look at your notes, look at the examples, rewatch the video if you need to, it's the same process. There's nothing changes, nothing is tricky. It's just a matter of understanding and doing each of the steps and getting it into your calculator correctly. Once you get past the first test, there will be a variance and standard deviation calculation on the first test, and of course on your homework for section 3-2. But once we get past that, you don't have to calculate these by hand anymore. You can either use, I'll show you an online program you can use, or when we get to that point, or you can use your calculator if you have like a TI graphing calculator, or it'll be given in the problem. Most of the time it's just going to be given in the problem, but you're not going to have to calculate it. You just, section 3-2, we learn how to calculate it so we kind of understand what it is, and then for the rest of the class, mostly we just utilize it. Okay, so how do we do the shortcut formula? And this is what I want you to use on your homework. Okay, so now that we kind of understand where all of this came from, we're going to use this on your homework. Okay, so the first one is s squared, and the second one is just s, and you can see again the only difference between s squared and s is that s has a square root over it. So to get from s squared to s, we just do a square root. And that gets rid of the square on the s, and we've already got this value calculated. Now this looks longer, but this is what's nice about the shortcut formula. The shortcut formula, if you notice, does not use mu or x bar in it. In this case it'd be x bar because we're doing sample. But there's no x bar. And so what's the benefit of that? Well, remember, if we had a average and we were subtracting it, let's say that average had been rounded. Well, every time you subtracted, then that answer would be rounded. And then when you squared them, those would be a little bit off. So sometimes if our x bar doesn't come out perfectly, a nice whole number, and we have to round it, or even a decimal that we have to round, that error, that rounding follows all the way through the problem. We don't have that in this case. And so it's actually, in a lot of cases, more accurate than the what we call the theoretical method. And why does this work? We don't have to worry about that, okay? A mathematician at some point, a statistician, determined that this formula gets you the exact same answer, and it's easier, and so this is what we use. We call it the shortcut formula. It's on your formula sheet. Let me pull up the formula sheet really quick while we're talking about that. Okay, so this is the formula sheet that I have referenced, and the formula sheet is available several different places. So it's in D2L. I have a PDF of it on our D2L page, so you can utilize it from there. You can download it and print it. It's also in Alex. I think it's with the ebook. It's either with the ebook or it's like in the same area but separate. And also, why is it not responding? There we go. Or you can also, when you take your exam, it's within the exam, you can open it up. So this is the formula sheet that you can use on all your exams. You don't have to memorize any of your formulas. And so the formula that I was just referencing is right here. So you'll notice it's on the formula sheet. You don't have to memorize it. You just have to know what all the variables are. So in this case, remember I said you've got to know what the variables are. You have your formula here, but if you have to know what n is, you have to know what sigma x squared means, what sigma x means. Again, you have n's and n minus 1s. You have to know what all this means, and then you have to know that s is the standard deviation for the sample. I mean, it says it right here also, but you have to know that's the formula I need to use. You don't have to memorize the formula, but you have to know that's the formula I need to use, and then you have to know what all the variables mean so you know what to calculate. Okay, so this can be utilized on all your exams, and you can find it again in D2L. It's got its own module in D2L. You can find it in Alex, and you can also open it on the exam. If you prefer on the exam, you can also print it out ahead of time. But before the exam starts, you're going to have to show that printed formula sheet and show that it doesn't have any extra writing on it or anything. Okay, you can't write anything extra. It's not like an open note, take all the notes you want test. You can use this formula sheet as printed. Okay, so let's close this up. And let's practice using this shortcut formula. So the shortcut formula, again, just uses n, which is the number of values in the data set. It uses the sum of the x squares. So the sum of the x squares means you square the x's and then sum them up. And then this other one that looks very similar to it, but it's not exactly the same because the square's on the outside. So you see here the square's on the inside, and on the second one the square's on the outside. This means you sum the x's and then square it. And then the bottom is n and n minus 1. So you're going to take whatever the number of values are and then multiply it by one less. So like for the candy, we would have taken 5 times 5 minus 1, or 5 times 4. So let's do that with a practice problem here. We're going to use the bags of candy again and use the shortcut formula. So we've got our 5 bags of candy, and to get this value right here, we're going to do the x squares. So the x squares are 34 squared, 38 squared, whew, what's wrong with my pen? 38 squared, 39 squared, 41 squared, and 43 squared. But remember, what we want is we want the sum of the x squares. So instead of being commas in between here, what we're going to do is we're going to actually add them up. And you don't have to write down these values individually. You can just put this on your calculator and add them up. I don't need to know exactly what 34 squared is. You can just add them up and get a final answer. So we'll do that. So in this case, we're going to do 34 squared plus 38 squared plus, sorry, it's got that darn prompt on there about whether I'd recommend it to a friend. 39 squared plus 41 squared plus 43 squared, and we hit equals. Okay? And that gets us 7,651, 7,651. These are usually pretty large because we're squaring everything. All right, so if I square these and add them, I get 7,651. The sum of the x's is much simpler. That's just 34 plus 38 plus 39 plus 41 plus 43. That comes out in this case to be 195. Okay, so just a straight addition of the 5 numbers. So now these are the 2 numbers that I need for my formula. So the s squared, which is the variance, is n times the sum of the x squares minus the sum of the x's squared over n times n minus 1. So what is n? Well, n is 5 because there were 5 bags of candy. The sum of the x squares, that was 34 squared plus 38 squared and so on. That's the 7,651. Then I'm going to subtract the sum of the x's squared. The sum of the x's was the 195. And then I still want to square that, but I do that after I've added them like I did here. Then I'm going to divide by n again, which is 5, and then n minus 1, which in this case is 4. So 5 minus 1 is 4. And that's what I compute. What I would highly recommend on this, you can try to do it like all the way through if you want. If you do that, you're going to have to put like extra parentheses here and here when you put it in. But I would instead recommend that you just do them in parts. So I would recommend that you do the bottom. You can usually do in your head. So 20. And then on the top, just type in what the top is and compute that. So we're going to get 5 times 7,651 minus 195 squared. And that gets us 230. So we get 230 over 20. And when I divide that, I get 11.5. Remember, we already know the answer to this because we already did the theoretical method. Now, I think if you look at that, I think that's easier. Because remember, with the theoretical method, we had to calculate the average, then we had to subtract each one from the average, and then we had to square all of those and add them up. It's just kind of hard to keep track of. I think this one's a lot easier to keep track of. Just square them all and add them up, and then add them up, put everything into the formula, and you've got it. And you get the same answer you can see. And then we found before, of course, that if we want to do the s, that's just the square root of the s squared, which is, in this case, approximately 3.4. So we get the same variance and standard deviation that we got before. Okay, so we're almost to the end of this section, I believe. Let me double check. We have a little bit left, but we're through kind of the heart of this section. Again, this is probably one of our more difficult sections, so don't get discouraged or frustrated and think it's just going to get worse and worse from here, because this is one of our more difficult sections with the standard deviation. So when do we use the standard deviation and the variance? Well, they can be used to determine the spread of the data. As we mentioned before with the 2 paint brands, if you have a larger standard deviation, then the data is more spread out. So the standard deviation of the first brand, I think it was 17 something, and the second one was, let's go back and look. So we knew that the first brand was more spread out, not just from looking at it, but because it had a standard deviation of 17.1 and brand B had a standard deviation of 6.5. So the smaller the variation, or the smaller the variance, the smaller the variation or the spread of the data. So that's one thing that we can use. And then Also, variances and standard deviations are used to describe the consistency. The values of a random variable with a small variance tend to be roughly the same. So again, like brand B, when you have a small variance, it means the data is closer together. They're all close to the same center. They also determine what proportion of the values in a data set are within a given interval. We'll learn that here next with the Chebyshev's theorem, and then we'll further look at that when we get to a later chapter and start talking about normal data. And then variances and standard deviations are used in inferential statistics, like to make predictions and generalizations of the population. Okay, so the next thing that we're going to talk about, we have two things to talk about. We still have to talk about the coefficient of variation and what's known as Chebyshev's rule. So the coefficient of variation is the standard deviation divided by the mean for a set of data. And when do we use that? What do we use that for? Well, we use the coefficient of variation when we want to compare standard deviations with different units or wildly different values. So they could both be, say they're both measures of money, but one is small amounts of money and another is large amounts of money. But very often we have two completely different units of measurement. And so you're trying to look at these and you're trying to say which one of these varies more. You can't just look at the standard deviation and say that they vary more when they have different units. And so here's an example where we have different units. So let's say Dean owns a family pizza shop, okay? Over a 3-month period, he found the mean cost of a pizza order was $32 with a standard deviation of $5. So took all that data, computed it, and found that the mean cost is $32, the standard deviation is 5. We don't know if he did the entire population or if he did that using a sample. It doesn't really matter. We have the data. That's all we need. While the delivery distance, the average delivery distance, mean delivery distance, is 1.22 miles with a standard deviation of 0.25 miles. So how do we tell if the pizza order cost varies more or less than the miles driven? It's very hard to compare because one's measured in dollars and one's measured in miles. But we can do that using CVAR. And so the CVAR, the coefficient of variation, all we have to do is for the pizza, we take remember, let me go up here really quick. Remember, it's the S over the X, okay? So we're going to do, for the pizza order, we're going to do S over X bar, and then we're going to multiply it by 100 to get a percent. Okay, so in this case, for the pizza, the S is 5. Remember, that's the standard deviation. And then the average cost, the X bar, is 32. So 5 divided by 32 times 100 gets us approximately 15.6%. Then if we do the same thing for the delivery distance, so that's for the cost, now for the delivery distance, we know that the S for the delivery distance is 0.25 miles. And we know that the average delivery distance is 1.22 miles. And if we multiply that by 100, we get about 20.5%. Now, if we just looked at the standard deviations, $5 is big, 5 is bigger than 0.25. But when we use the CVAR to kind of balance things, it's like, we took apples and oranges and we made them both fruit so that we could compare them. So we're trying to compare these two using the CVAR. And in this case, we can see that actually the delivery distance varies more than the cost of the order. So delivery distance varies slightly more variable than the cost of the order. So whichever one comes out with a bigger percentage, that is the one that is more variable. And we're changing it so that we are comparing the two to each other without worrying about the units. So we're comparing the standard deviation to the average from that, and then the standard deviation to the average from that. So basically, how much of the average is the standard deviation? And that gives us this percentage. So 15%, 5 out of 32 is 15% of the average, whereas this is 20% of the average, and so this has more variation. It's more variable. All right. By the way, I almost always put one of these on the exam. So expect that to be on the exam. You'll have the formula. That's one that the formula is not on the formula sheet, but if I ask it on the exam, I'll give you the formula. I won't make you memorize that. All right, so measures of variation. So we're going to talk about what's known as Chebyshev's theorem. So Chebyshev is a mathematician or a statistician, and he discovered or proved that you could determine a certain percentage of values that fell within a certain number of standard deviations. So I know that doesn't make a lot of sense. So let me give you an example. So let's say that we had, let's use our pizza example, okay? So remember the example for the pizza was that orders were $32 on average, and then we had $5 for the standard deviation. I'll assume it was a sample. Doesn't really make a difference. Okay, so we're going to look at this on a number line. All right, so if we take this data and we put this on the number line, the average is 32. That's our X bar. Then I can mark off the standard deviations. So I'm going to mark off, this table goes to 4, so I'm going to mark off 4 standard deviations. So 1, 2, 3, 4. And then 1, 2, 3, 4. Okay, so what does it mean to be 1 standard deviation? So plus 1 standard deviation. Well, that means I'm going to add this $5. So there's 32 in the middle. 1 standard deviation would be $37. And then I'm going to add 5 again to get to 2 standard deviations. So that would be $42. And then I'm going to add 5 again to get to 3 standard deviations. And that would be $47. And then 4 standard deviations would be plus 5 again, so that would be $52. So each time that you go up 1 standard deviation, that means you're going up $5. Now we can do the same thing in the opposite direction. If I go down 5, then I get minus 1 standard deviation, which would be $27. Go down 2 standard deviations, that would give me $22 because I go down another 5, so 27 minus 5. 22 minus 5 would be 17, and 17 minus 5 would be 12. Okay? So what did Chebyshev determine? Well, he determined that if you have a set of data, it doesn't matter how it's distributed, it could be symmetric, it could be skewed, it could be any type of data, and he determined that you can use this formula to find the minimum percentage of data that has to fall between 2 of the matching standard deviations. So we're going to start off with the 2 that he used here. So 1 minus, for his formula, 1 minus 1 over k squared for 2 standard deviations. So k equals 2. Okay, so we're doing this first row here. So k equals 2 would be 1 minus k squared would be 1 minus 1 over 2 squared, or 1 minus 1/4. So that's where this comes from, this 1 minus 1/4. It's 1 minus 1 over 2 squared. That's 3/4, which is 75%. Okay, so let me mark that up here. And I'm going to mark it, I'll do it here. Okay, so from 2 standard deviations to 2 standard deviations, the absolute minimum amount of data that has to be between $22 and $42 for Dean's Pizza Store is 75%. So 75% of the data values had to fall between $22 and $42 in Dean's data set. If they didn't, it would have a different standard deviation. So we know from Chebyshev's theorem that there has to be at least 75% of the data values that he had that were between $22 and $42. Okay, so I'm going to rewrite this because I wanted to get this out of my way. Okay, and then if we do the same thing for 3, we have 1 minus, so if our standard deviations is 3, plus or minus 3, so we're going to be going from here to here, right? Then if we do that, we're going to do 1 minus 1 over 3 squared, which is 1 minus 1/9, which is 8/9. So that's this one right here. Now I'm just going to round this to make it easier. They say 88.89. I'm just going to round it to 89%. It'll make it easier on our picture. Okay, so from here to here, Chebyshev said the minimum amount of data values that are within 3 standard deviations are approximately 89% of the data. So about 89% of the data values have to fall within 3 standard deviations. Then we do the same thing for 4. So this is 1 minus 1 over 4 squared, or 1 minus 1 over 16, and that comes out to be 93.75. Okay, so again, I'm going to round that just for ease of, we'll call that about 94%. Okay, so 94% of the data has to fall within 4 standard deviations, no matter how the data is distributed. It can be, again, skewed, symmetric, consistent, it doesn't matter. And this was really important, actually, because it showed researchers or statisticians that almost all the data, 94%, is going to fall within 4 standard deviations no matter what. Now, why do we not have 1? Well, let's back up and do 1. So if we have 1 here and we use his formula, that would be 1 minus 1 over 1 squared, which would be 1 minus 1 over 1, which is 1, which is 0%. So his theorem also supports that within 1 standard deviation, there could be none of the data. Okay, the data could all be, like for Dean's situation, he could have all orders in his sample that are above $37 or below $27. There doesn't have to be any that are between 27 and 37. Okay, so between 27 and 37, Chebyshev said, I can't guarantee there's going to be any in there, but 75% of the orders will be between $22 and $42, 89% will be between $17 and $47, and almost all of them, 94%, will be between $12 and $52. Okay, now let's look at the example and let's look at their graph. So this is the same thing we just did. It just has it with, let me close this thing. Yes. Okay, so it just has it with generic instead of having actual numbers in there. So on our example, the X, remember, was 32, and then they don't mark -1 because it was not in the table, but you know, -1 would be here, And then they have minus 2s, minus 3s, plus 1s, and then plus 2s plus 3s. So it's just generic instead of having specific details like ours. But on ours, this was 32, this was 27, this was 22, and this was 17. And then they don't even have 4 on here, but... Okay, so what does this look like as an example? And this is our last, remember, this is our last thing. I know this has been a long section. So this is our last thing for section 3.2. And on the exam, when I ask these questions, I always stick with, if you can remember or keep in mind, again, that there are, plus or minus, within plus or minus 2 standard deviations, that's the 75%. Within plus or minus 3 standard deviations, that's the roughly 89%. And then within plus or minus 4 standard deviations, that's the roughly 94%. If you can remember that, you'll be fine. You don't have to, I'm not going to give anywhere the K is like 2.5 or 3.5. Your homework problems might, but I won't on the exam. Okay, so on this one it says the mean price of houses in a certain neighborhood is $50,000 and the standard deviation is 10,000. Find the price range for which at least 75% of the houses will sell. Now, they go into the formula for this. My biggest recommendation is use that drawing technique that I just used. People can see that and understand that so much better. So let your, give your brain a break and let it see the picture for this. Okay, so we have the mean price of houses, it says, is 50,000. I'm going to just do 50. Okay, so 50,000 is right in the middle. And the standard deviation is 10. So that means I have 60,000, 70,000, 80,000. And then, just take this out a little bit. And then we have 90,000. So this is our average. Mark this with average, so X bar. And then this is plus 1s, plus 2s, plus 3s, plus 4s. And then do the same thing on the other side. So 40,000, 30,000, 20,000, 10,000. And that's minus 1s, minus 2s, minus 3s, minus 4s. Now, he wants to, or the question asked, at least 75%. Well, we need to remember, as I said, if you can just remember these three, that within 1 standard deviation there was 0. That's not going to be helpful. But within 2 standard deviations, that was the 75%. So 75% is within 2 standard deviations. So what is 2 standard deviations? Well, 2 standard deviations is the 30 to 70 on our graph here, on our number line. And so that's the answer. Between 75% of the houses will fall between 30,000 and 70,000. But it's much easier, I think it's much easier for students to understand with the picture. So that would be my recommendation. Okay, so let's do one more example and we'll call it done for section 3.2. So this one kind of does things in reverse. It kind of asks the question backwards. It says a survey of local companies found that the mean amount of travel for executives was 25 cents per mile with a standard deviation of 0.02. Use Chebyshev's theorem to find the minimum percentage of the data that will fall between 20 cents and 30 cents. So again, draw the picture, because the picture, it doesn't really matter which angle you're looking at it from, it's still easy to visualize. Okay, so if we go from our number line on here. Okay, and I don't know why that won't go away. There we go. That keeps popping back up. Okay, so if we have our number line here, and we're going to put our 25 cents in the middle because that's our average. And then it says the standard deviation is 0.02. So our measurement distance between standard deviations is 0.02. So 25 cents, 27 cents. Next one would be 29 cents. Next one would be 31 cents, and then 33 cents. So I just again went up by 0.02 each time. So this is +1, +2, +3, +4 standard deviations. And then if I go back this way, I get 23 cents, 21 cents, 19 cents, and 17 cents. And that is my -1, -2, -3, and -4. So now let's look what the question asks. It says minimum percentage of values that fall between 20 cents and 30 cents. So we'll look on our chart, and I see that 20 cents to 30 cents is here to here. Okay. And so that's between -2.5 standard deviations and +2.5 standard deviations. For Chebyshevs, we have to have them even like that. You can't do like down 2.5 and up 1.5. So down 2.5, up 2.5. So I'm going to, this is again one that could be on your homework, but I wouldn't ask one like this on your test because I'm going to stick with just -1, -2, -3, -4. So, so that you can use the 75, 89, 94 percentage. But on your homework, you might have one on like this. And so what we do for this is we take and we say, okay, well, I can see that's -2.5 for the S. So I'm going to use the formula. 1 minus 1 over 2.5 squared. We know it's going to be somewhere between 75% and 89% because 2 is 75% and 3 is 89%. So it's got to be somewhere between these two values, but it's not going to be exactly between them. So I'm going to calculate this and get 1 minus, I'll show you how to do that on the calculator. 1 minus 2.5%. We're just going to do 1 minus, I'm going to do this as a fraction. See this button right here? That'll pop up fraction, n over d, numerator over denominator. And then I just put in a 1 on the top. And then on the bottom, I have to arrow down to it. And I do 2.5 squared. And hit equals. And I get 0.84. And so you can see the answer is at least 84% of the data values will fall between 20 cents and 30 cents. Okay, so that's it for section 3.2. Hopefully you'll be able to tackle and be successful with your Alex homework for section 3.2. And I will see you back for section 3.3. This chapter is very similar to chapter 2, where the second section is the kind of the heftiest one, and then the last two sections are a little bit easier. So in this section, or this chapter for certain, section 1 and section 2 are bigger. Section 3.3 and section 3.4 will definitely be shorter. Have a great, good luck with your Alex, and have a great rest of your day.